Very good. Thank you very much. I would like to thank the organizers. In particular, I would like to thank Rama. Is she here? No, not yet. For inviting me. It's my first time in India, and I'm enjoying it tremendously. So it's a wonderful trip so far. I hope it's not going to be my last time here. The organizers, I should say, also did a great job in terms of setting up a perfect schedule. So it was wonderful how Emily set the stage for oceanic applications, and I would like to go a little bit more into that, and in particular talk about how sedimentation processes can contribute to turbulence in the ocean. So the problem that we're interested in is the one where we have a river flowing into the ocean. So the river typically consists of fresh water and it carries some sediment, but this combination of fresh water and sediment together is lighter than the salt water of the ocean under most conditions. And so that means the river water with the sediment forms a buoyant plume, so it propagates along the surface of the ocean. And we're then interested in the question of how the sediment settles out from this buoyant river plume and reaches the seafloor. That's a very important part of the global sediment cycle, and so finding effective sedimentation rates is a problem of significant interest. And as it turns out, in many oceanographic models these days, the settling velocity is approximated by the Stokes settling velocity. And as we will see here, often that's not a very good approximation because additional phenomena can become important, the settling process can become turbulent, and then the settling velocity effectively can be quite different from the Stokes settling velocity. So let's talk about that in detail. So if we focus on this situation and we reduce it to kind of the simplest possible scenario, then we have a sketch here like this. So we have here the seafloor, here we have the river, so fresh water and sediment flowing into the ocean, and then we have the salt water below. And as I mentioned, the fresh water and sediment is lighter than the salt water, so this is stably stratified, and we're interested now in the processes in this interfacial region here. So if we look at the base density profile, we have this combination of fresh water and sediment, which is lighter above salt water, which is denser. And so at first glance, you might think, well, this is a pretty stable configuration, so there shouldn't be much interesting happening. However, interesting things can happen in various different ways, and those are things that we want to discuss now. First of all, we have now with the sediment and the salinity, we have two scalars, if we think of the sediment as a sediment concentration field. So we have two scalars that contribute to the overall density of the ocean. And these two scalars have associated with them effective diffusivities. So salt has an effective diffusivity, a molecular diffusivity in water, and we can think of small sediment particles also having an effective diffusivity, and that diffusivity typically is much smaller than that of salinity, so that these two scalars diffuse at very different rates. And that can lead to some interesting effects. So let's look at the little thought example of displacing an element of fresh water and sediment into a saltwater surroundings. So then what we will see is that now, because the sediment diffuses so much more slowly than the salt, we have a lot of salt diffusing into this fluid element, but very little sediment diffusing out of this fluid element. And so that means that very soon this fluid element will be carrying both salt and sediment, so that it will now be denser than the salt water without the sediment that surrounds it, and so it'll keep sinking. So that's the effect that's known as double diffusion. So it's related to the fact that we have two scalars with different effective diffusivities, and that can lead to an instability even when the overall density profile is stable. So that's then a situation where, as I mentioned, this perturbed fluid element will keep sinking down, so the instability will grow. And people have looked at this effect in experimental setups, in laboratory experiments, exactly at this configuration. So having fresh water and sediment above salt water. And when they were using fairly small sediment grains, then this is what they saw. And you see indeed here, this interface goes unstable. And we have these plumes of sediment that descend down into the saltwater environment. And this looks very similar to images that we know from the traditional case of double diffusion, which is double diffusion involving heat and salt rather than sediment and salt, which is known then as thermohaline diffusion. And that gives rise to very similar structures to this. However, what Parsons, Bush, and Savitsky also observed was that when they took somewhat larger sediment grains, then the picture no longer looked like this, but it looked like this. We have now these very sharp, wispy structures protruding down from the interface, rather than this space-filling pattern of convective fingers. And so they term this the leaking mode. And what we want to do now is we would like to see if we can understand the difference between what governs a flow of this mode and what governs a flow of this mode. And what we'll do in order to make some progress towards understanding that is carry out both some DNS simulations and also some linear stability analysis. So I had already mentioned that double diffusion is one of the mechanisms that can trigger an instability in this interfacial region. There's a second mechanism that can trigger such an instability, and that's related to the effect of the settling velocity. So we know the sediment has associated with it a Stokes settling velocity, and as a result, right at the interface between the salt water and the fresh water, the sediment settles from the freshwater region into the saltwater region, so that now at the top of the saltwater region, we have both salinity and sediment in the fluid. And that means that now we have truly a density overhang. So we refer to this as our nose region. So we have a density overhang, higher density above lower density. And so that should have the potential of giving rise to a Rayleigh-Taylor instability, right? So we see the possibility to generate a Rayleigh-Taylor instability here, which is not related at all to different diffusivities. And then we saw earlier the possibility of having a double diffusive instability, which is not at all related to the settling velocity, right? So two very different mechanisms that can contribute to instabilities here in the interfacial region. So as I mentioned, we want to do some DNS simulations, and we want to do that in the simplest possible way. So we take the incompressible Navier-Stokes equations in the Boussinesq approximation. We assume that the density varies linearly with the salinity content and the sediment content. So then we have as our equation here the incompressible continuity equation. We have the Navier-Stokes equation with the gravitational term. So this is where density variations will be felt, and this is where density gradients will drive the flow. Then we have a convection diffusion equation for the salinity field, and we have a convection diffusion equation for the sediment concentration field, where we assume that the sediment concentration field moves with the fluid velocity field, plus it has the superimposed settling velocity, the Stokes settling velocity, right? So the sediment is largely carried along with the fluid motion, but then it has a small differential velocity, vertical velocity, as a result of its Stokes settling velocity. In this problem that I described, we don't really have any external length scales that enter into it. And so as a result, we use viscous scales and buoyancy scales to make things dimensionless. And that then leads to 4 dimensionless parameters. The first one is a dimensionless settling velocity of the particles. So think of the Stokes settling velocity made dimensionless. Then we have the stability ratio. The stability ratio tells us how big the contributions to the density field are by the salinity field and by the sediment field. And of course, we're always interested in the situation where we have a stronger contribution from the salinity than from the sediment. And so that means this stability ratio is always larger than 1. Then we have the Schmidt number, which is the ratio of the kinematic viscosity and the diffusivity of the salinity. And finally, the diffusivity ratio of our two scalars, so of the salinity and the sediment. So these are the four dimensionless parameters that we need to pay attention to. So let me just show you some still pictures from a first two-dimensional simulation. So here time progresses from top to bottom, and in the left column we see plots of the sediment concentration field. In the right column we see the salinity field. And so in the beginning you see here we have all the sediment in the top half, all the salinity in the bottom half, and then we see already this instability developing along the interface here. And now as time goes on, we see these small growing fingers become larger and larger plumes. They start to interact with each other, they form collective motion, and eventually they extend across much of our flow field. We also see here that the concentration contours of the sediment concentration field are much sharper than of the salinity field. And you remember that's due to the fact that the molecular diffusivity of the sediment is so much smaller than that of the salinity. So that means our concentration contours here will stay much sharper than they stay for the salinity field. So these are just a couple of still pictures in order to show you the basic phenomena that are happening. And now we can look at a movie of a simulation like this. So it's exactly the situation that I described before. We have fresh water and sediment above salt water. We have an interface here initially that we perturb slightly in a random fashion, and then we'll see what instabilities those perturbations can trigger. So this is again the 2D simulation, left the sediment field, right the salinity field, and we see how we form this instability, how these plumes propagate upwards and downwards, and lead to a lot of turbulence generation in this interfacial region. We can then, I always like to think of vorticity as a quantity that drives the flow, that gives me some insight into what drives the flow. So we can look at the vorticity field and see how these plumes correspond to dipoles in the vorticity field that drive these individual flow structures and so on. So we can learn something from that. And then we can look at a fully 3D flow. And it's a very similar situation now. We see again this interfacial instability, both here in the sediment concentration field and in the salinity field. It shows a vigorously growing instability with plumes going upward and downward. Now we take a crosscut at the initial interfacial location through the sediment and salinity field, and we see these are the manifestations of these local plumes that are propagating upwards and downwards. And so we have these local plumes that go up and down that cause most of the vertical transport. Okay, I think that's been enough of this movie. So now we want to make some progress quantitatively, and in order to do that, what we do is we take horizontal averages in our 3D simulation. So we average concentration fields and so on across the entire horizontal plane, and that then gives us a one-dimensional vertical profile, and we can look at that one-dimensional vertical profile as a function of time. And so here we see the one-dimensional profile for the sediment concentration field. Here we see it for the salinity field. And we see initially, again, all the sediment is on top, all the salinity is at the bottom. But then as these instabilities grow in the interfacial region, we have this wedge opening up in time that reflects the effect of these plumes that propagate upwards and downwards and that lead to quite a bit of mixing. By the way, up here, you can see this gives you an impression of how large the Stokes settling velocity is. Up here at the top of our computational domain, we simply have a stable interface settling with the Stokes settling velocity, and you can see that this settling motion here is much, much slower than the rate at which these plumes propagate in the vertical direction here, right? So now we can take these one-dimensional vertical profiles and we can fit error functions to them. And these error functions then allow us to associate a center, so an inflection point of the profile, with the profile, and also a thickness, right? So we can talk about an effective thickness and an effective location of our profile. And we can then look at those things as a function of time. So here we see that these error function fits work quite well. Here we have the sediment concentration field for 3 different times. The solid line is always the computational data, and then the dashed line is our best error function fit. And we can see how, as time goes on, the profile becomes smoother, and the same thing also is true for the salinity. So those fits work quite well. So now if we look at the effective location of the sediment concentration profile, the center, so the inflection point location of the profile as a function of time, then we see that after some initial transient, so our computational data again are the solid line, and then the dashed line are a square root of time fit. And so we see after some initial transitional time, this square root of time represents a very good fit for the growth of this thickness, and that tells you that the growth of these interfacial regions is dominated by some effective diffusivity, right? Now, the interesting thing that we see is that the thickness of the sediment profile grows more rapidly than the thickness of the salinity profile. Now, remember, the molecular diffusivity of the salinity was much larger than the diffusivity of the sediment. So based on the molecular diffusivity, we would have expected that the salinity profile thickness should grow more rapidly. So the fact that in truth the sediment profile grows more rapidly, that tells us that it's really turbulent diffusivity that dominates here, not the molecular diffusivity. And then we can also track the center of these error function profiles as a function of time. And what that shows us then is that the center of the sediment profile kind of moves down with time. Initially, it moves down at the rate of the Stokes settling velocity, which is this dashed line. But then after these instabilities grow, it deviates from the Stokes settling velocity, and the salinity interface location actually moves upward. So what we see then here is this would be the height of what we call our nose region in the initial sketch. So this is the height of the fluid layer that contains both salt and sediment, and we see that that fluid layer becomes thicker and thicker with time. Okay, and then if we look at the ratio of the height of this nose region, so this H here, the ratio of that to the effective thickness of the salinity interface, which here is a step profile, then we see that this ratio approximates a value of around 0.1, which stays quite constant with time. So that means this sketch here is not at all accurate. What I should have drawn is I should have drawn a very smooth salinity profile. So a salinity profile that has a much larger thickness than the thickness of the nose region here. So the nose region effectively stays embedded in this effectively diffusing salinity interfacial region, and that's the reason why double diffusion can remain important, right? Because both of these gradients are in the same location. So that's why this process is dominated by double diffusion. Now, if we look at the effective settling velocity, and that's of course what we want to get eventually, then we can again do this process that we average over entire horizontal planes in order to get a one-dimensional profile, and then we plot that as a function of time. And so this shows us the effective settling velocity, and we see here this large blue region which has an effective settling velocity on the order of -1. So that tells you that in this region here, the particles, the sediment, is effectively settling with a velocity of -1. So what does that mean? Well, -1 is actually according to the way we made things dimensionless, it's the buoyancy velocity of the system. So what this tells us is that the sediment effectively settles with the buoyancy velocity of the system rather than with the Stokes settling velocity. The Stokes settling velocity in this case was 0.04, so that is much, much smaller, and we find that the sediment settles effectively with 1, so 25 times larger than the Stokes settling velocity. So that shows you how this instability and the turbulence that's being generated in this interfacial region really speeds up the effective sedimentation rate of the particles, so that estimating that rate with the Stokes settling velocity would not be a very good approximation. So then we performed a second simulation in order to see if we could reproduce this other mode that had been observed experimentally. And you remember that other mode was observed when the sediment size was a little bit bigger. And in our approximation here, the way we have formulated our equations, sediment size just corresponds to effective settling velocity. And so we want to see if now we can get these very wispy structures. And so now we see a very different behavior from what we saw before. We see plumes propagating only downwards, not upwards for this larger sediment. And we do indeed see these concentrated structures here at the interface rather than these space-filling fingers that we had seen before. This is when we look at this interface, look at it from above and from below. We see again these plumes. But there's now a big difference. If we now cut again at the location of the original interface, we see initially these plumes forming, but then we see a topological transition into a web-like structures, which tells us that effectively now the dominant structures have the form of sheets rather than fingers, rather than local plumes. And so with these sheet-like structures, you can imagine now if you put a light sheet through one of these settling particle sheets, then you get this very localized wispy structure. And so that explains the experimental observations of Parsons, Bush, and Savitsky. So we then did a number of simulations like this for different parameters. And to make a long story short, we were able to collapse all of these results in the following way. We can plot this ratio of nose height or nose thickness over the salinity interface thickness. We can plot that as a function of this dimensionless grouping here, which you can think of effectively as the particle size in some sense. So down here we have small particles, up here we have large particles, and if we do that, then all the results collapse onto this one line. And so what that tells us is that for small particles, we have a relatively small nose height. For large particles, we have a larger nose height. And so that allows us then to come up with a good physical interpretation of what's happening with these two different modes. Namely, for small particles, so for small settling velocities, the settling rate from above, which is given by the Stokes rate, is fairly low. And so that means particles are settling into this nose region in a fairly slow fashion. And so this low influx of particles into the nose region, that can easily be gotten rid of downwards by double diffusion. And so as a result, the height of the nose region remains small. There's not much accumulation of these particles. Whereas if we have a larger settling velocity, so larger particles, then particles settle more rapidly from above, and so they enter the nose region more rapidly. And because this inflow of particles into the nose region now is more rapid, double diffusion is not strong enough to get rid of these particles down below from the nose region. As a result, particles accumulate in the nose region, and the nose region grows in thickness, and it grows until it is thick enough so that a Rayleigh-Taylor instability can set in. And then this whole layer, this unstable nose region, just turns over in these violent and vigorous Rayleigh-Taylor motions. And that, again, then provides a strong enough mechanism to get rid of all these particles downwards. So those two instabilities, the double diffusive instability and the Rayleigh-Taylor instability, explain these two modes that have been observed experimentally. Okay, so what I've discussed so far is the situation where we start from a sharp interface with fresh water and sediment above, salt water below. Typically, of course, in the ocean, we have more distributed profiles rather than sharp profiles. And so we then decided also to look at this second case, which is equally interesting. And so in this case, we start with linear base state profiles rather than sharp interfacial profiles. And so we have, again, now I call it temperature, before it was salinity. So we have a stable temperature stratification that is linear, an unstable sediment concentration that is linear, and together that gives us a stable density profile. And so we want to look at the linear stability of this situation now. So we can perform a linear stability analysis. Essentially, we have the same equations as before. We make them dimensionless a little bit differently now. But again, we have these four parameters: a Prandtl number, diffusivity ratio, settling velocity, and stability ratio. And if we do the linear stability analysis, we actually obtain a very simple situation where we can just write down a cubic polynomial for the complex growth rate, lambda, which has a real part and an imaginary part. And these coefficients, A0, A1, and A2, are given here. So we can then determine this complex growth rate as a function of these dimensionless parameters, and that provides us some insight into what's happening. Let's first look at the situation where tau, remember tau is our diffusivity ratio, where tau is 1. So here we assume that temperature and sediment diffuse at the same rate, so there's no potential for double diffusive instability, right? So in the situation where we would have no settling velocity, this would be a stable situation. But what we see, as soon as we increase the settling velocity slightly, we do generate an instability. What is shown here? We show here contours of the real part of the growth rate as a function of the horizontal and the vertical wave numbers of the perturbation. So we do a normal mode analysis with the perturbations that are periodic in the horizontal and vertical direction. And so we can plot the growth rate as a function of these wave numbers, and we see these two unstable branches emerging here. And as we make the settling velocity larger, these branches grow. And it's always these two symmetric branches, which tells us that we should expect to see a pair or pairs of oblique waves that are inclined in opposite direction. So that's now a very interesting result, I believe, because this is a new instability. This instability was not known before. It's not related to double diffusion, because our two diffusivities are the same. It's simply triggered by the particle settling. So what drives this instability? Well, in order to understand what drives this instability, it's again good to look at the vorticity equation. We can write the vorticity equation in this form, where we can essentially say vorticity is being generated as a result of horizontal temperature gradients and horizontal sediment concentration gradients. And so when there is no double diffusion and no settling, then these horizontal temperature and sediment concentration gradients will always be co-located. And because the overall density profile is stable, that means the stabilizing temperature contribution will always outweigh the destabilizing sediment concentration everywhere, and as a result, the system is stable. But if we have a settling velocity, that means our sediment concentration field now will be shifted relatively to the temperature field, and as a result of this shift, the stabilizing effect of the temperature field might not be able to overcome everywhere the destabilizing effect of the sediment concentration field. And so here we show the eigenfunctions. You can see here the shift between the temperature eigenfunction and the concentration eigenfunction. as a result of the settling velocity, and that gives us this vorticity eigenfunction, which then leads to the growth of this instability. So let's do some DNS simulations in order to see what these instabilities look like. Here again, some still pictures. So this is again the case for tau equals 1. I'll just take about 3-4 minutes, yes? So tau equals 1, so that means there's no double diffusion here. So this instability is driven only by settling. We start from random initial perturbations, and we see that indeed after some time we have these pairs of oblique waves. These waves then generate secondary shear instabilities, and eventually, after a long time, we see this horizontal layering mechanism appear, which is quite interesting. So let me show you a movie of this simulation. So we start with a random initial perturbation, and then we see how this small random perturbation results in these oblique wave pairs, and then we see the secondary instabilities of these layers that form, and eventually a reorganization into horizontal layers after a long time. Now you see these horizontal layers emerging. So this was the case where, again, the entire instability is driven by settling. There's no double diffusion here because tau equals 1. Now let's look at the situation where tau is not equal to 1. So now we have the potential both for double diffusion and for settling-driven instability. And so if we now look at the situation where we have no settling velocity, then we only have double diffusion. This is now our unstable region, and the only unstable mode is the so-called elevator mode, which is marked here by an X. That's the most unstable mode. If we increase the settling velocity to 1, it's still this elevator mode that is most unstable. If we increase the settling velocity further to 2, then we see that now we again have these oblique wave pairs. And so now the settling-driven instability has become dominant. Yes, I won't be going into these details. Let me just show you this movie. So this is again now a situation that would be linearly stable if there was no settling, but, oops, it's happening. But with the, oh, okay, it's moving. With the settling, a strong instability develops, and then secondary instabilities, and so we see quite vigorous turbulence. Okay, a brief kind of back of the envelope estimation of the characteristic quantities would suggest that in the ocean we typically would get from the settling-driven instability a wavelength of about 60 centimeters. So that suggests that it's not totally out of the world, that this might indeed be important under real conditions. So let me then just summarize. So we saw that sedimentation in fluid from rest can give rise to these turbulent instabilities via various mechanisms. It can either be double diffusion, it can be a Rayleigh-Taylor instability, and this new settling-driven instability that we identified. And in particular, of course, this new instability was of interest to us. We found through this linear stability analysis that it amplifies in a preferred fashion these inclined waves. We could nail down the physical mechanism that drives the instability to this phase shift that's being generated as a result of the settling velocity. And we saw some interesting competitions between double diffusive and the settling-driven instabilities, and DNS simulations confirm these results. What we're now looking at, of course, is trying to make the situation a little bit more realistic for the real ocean, because in the real ocean, you also have shear. And so we can have a competition between these instabilities here and the shear instability that you would have in the ocean. And so that's, again, an interesting question to look into. One of the questions there is, can a HOMBO instability form? So I think there's lots of room here for additional work. But the main point that I wanted to get across is that the dynamics of sedimenting particles by themselves can give rise to turbulence in an oceanic environment. Thank you very much.
Thanks a lot, Professor Meiburg, for this excellent talk. We have time for a couple of, or maybe 3 questions.
Yeah, really interesting. How important is preferential concentration in these cases? I'm wondering whether including something like Ferris-Balachandar term for settling.
Right. So here, what we did, we assumed that we have small particles, small sediment particles, and that allows us to neglect particle inertia so that we could assume that the sediment moves with the fluid velocity plus the Stokes settling velocity. And that means we don't have, because the fluid velocity field is incompressible, that means the sediment velocity field is also incompressible. So no preferential concentration here. But I agree with you, if the particles become larger, or if we also think of this as not just being a potentially important mechanism in an aquatic environment, but also perhaps for small rain droplets in air, where again you would have preferential concentration even for relatively small rain droplets, it's definitely something that should be looked at. I agree with you, yes.
So early in the talk you showed this different turbulent diffusion of salinity and concentration.
Right.
So naively speaking, you know, turbulent diffusivity, if it dominates over molecular values,
yes,
shouldn't they be the same, or am I missing something obvious?
No, they shouldn't be the same. Essentially, if you're familiar with the Taylor dispersion, you can think of it as something that applies in this context, that you have the fluid velocity field carrying these concentration gradients throughout, but then depending on the molecular diffusivity, these concentration gradients will locally smooth out again. And so it's this interaction between, on one hand, the local smoothing as a result of molecular diffusion, and then the convective transport by the fluid velocity field, that together dominates the turbulent diffusivity, and it's a function of both of them. No, you cannot really just add them. It's a little bit more complicated than that. Yeah.
Any other questions?
Has there been any study of the scaling behavior in the different regions as a function of the length?
The scaling behavior of these instabilities in?
No, of the scaling behavior of the structure.
Oh, no, not as far as I know. That might be an interesting thing to look at, yeah.
Yeah, if, for example, one could look at the universality classes.
Right.
Maybe KPZ or something.
Yes, I would be very interested to discuss this further with you, since that's something that I'm not so familiar with what one should do in that regard. So I'd like to hear your ideas.
Yeah, I was just wondering if you've done a simulation with multiple sized particles, and if you
not in this context. We have done that in other contexts. So in this framework of dilute and small particles and so on, essentially that can be done by taking a different concentration equation for each size of sediment. And so yes, that's something that can be done. And of course, the situation would probably be somewhat more complex, because each group of particles would behave somewhat differently. But yeah, yes, it's clearly that would again be one more step towards a real situation. Yes.
I just cannot resist myself from asking one question. That is, in these cases, there are a lot of this interfaces curvatures of different magnitudes. So in those regions, do you think this preferential diffusion or double diffusion can have some role, which can still amplify the concentration in those regions?
I mean, clearly, when we have
this in this interface, the interface is strongly curved, and the curvatures are of different magnitudes, the mean curvatures.
Yeah.
So in those regions, do you think that there can be preferential concentration of the sediments or the salt because of the differential diffusion effects?
You're right. So diffusion could lead to some gradient, some preferential concentration behavior. That's true. Yes. So convection cannot, because we have this incompressible velocity field essentially for the sediment. But you're right. Diffusive effects could lead to some inhomogeneities. That's a good point. Yes.
In the interest of time, we will move on to the next speaker, and let's thank Professor Meiburg once again for this talk.